So this is the object function for AUC maximization using hinge loss functions, and you can write down as a maximization problem over Zij here. So Zij is box constraints, Zij is between 0 and 1. And because Z and W is linear of this formulation, right? So you can use matrix language, use the inner product to represent the relationship between Z and W using a matrix, which is capital A here. So capital A is just actually related to Xi prime and Xj prime. And this G function, Gz, is just a summation of Zij here. And this formulation is very nicely connected to the conjugate concept in convex analysis. You can write down, this is exactly the definition of the conjugate function, which is denoted by G star. However, G star as a function, a conjugated function of a convex function is not smooth. So you cannot directly apply accelerated Naslov gradient method, which requires smooth conditions. To tackle actually this obstacle, in this paper, they using a smoothing techniques, which you add a strong convex function, which is denoted by dz, and you have a small smoothing parameter, which is mu, which is very small. And now you use this smooth actually function to approximate the G star, the original AUC object function. Because D is a strong convex, now you look at the conjugate function is smooth now. And then you can apply the accelerated Naslov gradient method to this smoothed actually object function. And an accelerated Naslov gradient method has a convergence rate, which is 1 over T squared here. Okay, so there's another method, which is extending the boosting algorithm to the setting of AUC maximization, which is called length boost. So the idea is also the same. You combine weak lengthening functions in order to build strong lengthening functions. So for handle stream data, online method is considered the liquid bound. The performance of online methods is measured by the liquid bound. So roughly speaking, liquid bound is just the differences between the cumulative loss and the best possible in hinge side. Mathematically, it can be defined as actually this RT here. So LT is just the loss of model W, WT at data XT and YT. So the summation is called cumulative loss. So this is the best actually decision in hinge side. A popular, of course, online method is called online gradient descent in the classical classification and the regression. In the seminal paper by Pei-Ling, Steve, and Rong and Tian Bao, they are the pioneers to study online buffer-based method for AUC maximization. So they proposed online AUC maximization algorithm for handling stream data in AUC maximization. The algorithm can be described as follows. The first, at the time t, you receive an example xt and yt. You will update your buffering set, which is denoted by curly b here. So based on some buffering techniques, which I will not talk about in detail here. So once you have a buffering set, which is usually of the small size of, let's say, is ACE. So you update the model parameter, which is here. And how do you do that? You will pair xt and yt with all previous examples. Not all previous examples, the previous examples from the buffering set at the time t-1. And then you compute the gradient information and you doing gradient descent here. And the degree bound is very nicely established in terms of these formulations. So B plus is just the size of positive examples in the buff set. And capital T plus denote the number of positive examples received at time capital T. And likewise for the definition B minus capital T minus here. And many studies in the following follow actually this similar work. So for example, for least square loss functions, Galway and his collaborators made a very important observation. The previous online AUC maximization only needs to update the two statistics. The first statistics is mean vectors. Mean vectors at time t for the class 1 and class minus 1. And also the covariance matrices for class 1 and class minus 1. Of course, because you need to update the covariance matrix, pay-attention cost and memory cost is still very large of the order of D squared, and D is the dimension of your data, right? So for high dimensional data, it can be efficient. So to overcome this disadvantage, they also use the low-rank approximation of the covariance matrix using Gaussian random matrix to reduce the complexity, of dimension for high dimensional data. For this type of algorithm, statistical bound is also studied in the literature. And statistical error is just to measure the differences between the performance on test data and training data. And various approaches is studied in the literature, including using coupling number techniques, Ledma complexity, and also the online AUC maximization is extended into kernelized version. So for example, in Wu's paper, it was extended into kernel method. In this work. And also gradient method for online AUC maximization. So to summarize the old school methods, usually these kind of methods use gradient type gradient descent and use the cutting plane method. Following the structure SVM formulation. So the main complexity is you need to compute the full gradient, or for the cutting plane method, you need to solve a quadrilateral programming as a sub-problem. So here sometimes you need a high memory and iteration cost because you need to retain the full gradient information. And the second type of method is online method, and it's efficient to handle the stream data, but also you need to pair with the example with the previous examples, current example with previous examples, and usually the performance is measured by liquid bound. Okay, so let me move to the second part. We want to design efficient optimization algorithms to handle big data. So in this part, I'm going to review the methods in terms of two settings. One is offline learning setting. In this setting, n data point is given, and we focus on the minimization for the empirical risk for AUC maximization. The second type of learning setting is online learning setting. So in this case, the data is arriving continuously according to unknown distribution. And in this case, the minimization of AUC maximization is formulated as a minimization of the population risk, which is FW here. In both cases, the theoretical studies focus on the statistical error. That is the population risk of WT, where WT is your output of your optimization algorithm, minus the least population risk. So this is the outline for AUC optimization for big data. And we will mainly talk about stochastic AUC maximization, because this type of algorithm can process the one data at one iterations, which is efficient to handle big data. In contrast, the online AUC maximization methods, which we talked about in the previous slides, this type of method usually assumes the data is IRD. I will divide this part into two main categories of algorithms. The first category is called stochastic batch-based pairwise method. And this type of method needs to sample a pair of examples. And the second type of method is called the stochastic primordial method, which you don't need sample a pair of examples. You only need to sample individual examples. So let me start from the first category, which is a stochastic batch-based pairwise method. So in this work in 2019, a double stochastic gradient method is proposed for the linear case. And in particular, this method has two steps. At each iteration, you will run SGD by randomly sample a pair of examples of size of n. So you're giving train data of size of m, you run SGD by randomly sample a pair of examples. You got a solution, and in actually second step, you use the solution obtained in the first step as a warm start to solve the next large problem. Let's say you have a train data now with size 2n. And kernelized AUC maximization and semi-supervised AUC maximization, we also started using SGD by randomly sample a pair of examples combined with the technique of random Fourier features. And all these studies focus on the online learning setting where the data is arriving continuously. And the convergence results are also established in these studies. For the on-fly learning setting, Yongwen and Minzui and I also study this pairwise approach. In particular, at time t, you will randomly sample a pair from all possible pairs of size. Train data is size of n, so you have all possible pairs, which is roughly n squared. So you randomly sample a pair of examples, you perform gradient descent here. And interesting is this simple algorithm has optimal statistical error. And we can prove that with high probability, optimal statistical error is 1 over radical n for the convex case, and for the low noise case, which means the population risk, the least population risk equal to 0, and the error rates can be 1 over n. And in last year, my student Zheng Huan and Tian Bao and me proposed another strategy to sample pairs from the existing from the individual samples. And this is called some kind of a Markov SGD, which can be described as follows. So let me describe it in the setting of online learning setting. So online learning setting, and the data is arriving continuously. So at the time t, you will see a data point ZT. And you will pair actually ZT with previous example, which is ZT minus 1. Okay. So, and then you perform gradient descent. And in this case, you will see ZT and ZT minus 1 as a random variable is a Markov chain. And then what you see is the follows. You can seamlessly extend it into an offline learning setting. And the offline learning setting is you have n data points, right? And you randomly sample IT at time t from this n data point. So this markup for SGD for AUC maximization is you will pair ZIT with ZIT minus 1. And IT minus 1 is the sample you sampled, as the random sample you sampled at time t minus 1. Okay, so this markup for SGD can apply both to online learning setting and offline learning settings. And also you can actually get with some very nice statistical error, which is 1 over let it go for n for the convex case, and for the low knowledge case, you can get a fast one, which is 1 over n. So in this series of works, by modifying the online AUC maximization in the seminal paper by Pei-Lin in 2009, you can extend the method to stochastic online version. So in this case, at time t, when you see a data point ZT, you will pair ZT with all previous examples, and then you perform a gradient descent. And also statistical error was established in this work. To summarize the batch-based pairwise method, usually you will adapt, depends on the pairing strategy. You can pair randomly sample a pair of examples, but this one is only works for the offline learning setting. You can pair the current example with previous ones, but it can be actually, the pairation cost can be very expensive because you have to pair the current example with all previous ones, right? A recent one is using Markov chain type. You pair the current example only with the previous individual examples here. And the statistical error is optimal, 1 over square root of t and 1 over square root of n for the offline learning setting. And these kind of studies mainly focus on the linear case and the terminal methods. Now let me move to the second category of stochastic batch-based method, stochastic AUC maximization. And for this type of method, we only need to sample individual examples. So to describe the method, I'm going to start with the AUC maximization with the least square laws. So here, FW is the scoring function, and this is object function, AUC maximization with least square laws. The main challenge to design algorithm is the double conditional excitation, because this is excitation with respect to xy, x prime, and y prime. And the data is continuously arriving as individual examples, not a pair of examples. So you cannot apply the standard actually SGD, directly. So to overcome this challenge, in this work, we reformulate the AUC maximization as a minimum maximum problem. More precisely, we introduce auxiliary variable, which is AB and alpha. It can be write down AUC maximization as a minimum maximum problem. The minimization with respect to WAB, maximization with respect to alpha. And the nice thing is the object function here now only involves a single expression with respect to Z here. And this function of Z is just defined in the following way, which can be found in the paper. And the nice thing is when we have the ranking function, FW is a linear function, and then we can show this problem is convex with respect to WAB and concave with respect to alpha. So based on this minimum maximum formulation, we can propose a stochastic online AUC maximization algorithm, which is basically is a stochastic primordial algorithm here. To be more precise, for this algorithm Solan, at iteration t, whenever you see a random example ZT, you will use actually compute the gradient at this data point and perform gradient descent for the primal variable, u. So u is WAB. And for the dual variable alpha, you do maximization. So you will use a gradient ascent here. So eta t is the step size. So you will see the per-iteration cost now it becomes actually at one data point to compute just gradient information on one data point. And we can show the convergence rate in the linear case is 1 over square. And the algorithm was also improved by my student, Mike Anatoli, in 2017, based on the following observation. For fixed W, the auxiliary variable we introduced in the minimum maximum formulation, A, B, and alpha, it can be write down explicitly for the linear case. So for example, for A, W, it is just the inner product of W and the conditional mean of class 1. And likewise for BW, and alpha W is just BW minus AW. Based on this information, we can propose the following method, which is denoted by span. So at iteration of t, you receive a random example ZT. You only perform the gradient descent for the W. Okay, so the W is just actually, you will compute AW, BW, and alpha W is just using this one. So this conditional expectation replaced by the empirical estimators and do gradient descent here. So the convergence rate is now improved to 1 over t if we have a strong convex case. And in the same year, Ming Rui and Tian Bao's group, they also proposed a faster AUC maximization for the with the least square loss function. They made a very important observation that the AUC maximization, after you maximize with respect to alpha as a function of WAB, satisfying a very important actually condition, which is called quadratic growth condition. So based on this information, they propose actually stage-wise SGD algorithm. Roughly speaking, this algorithm is this algorithm denoted by FSAUC a performance as follows. So you will perform the stochastic primal dual method with the shrinking search radius and shrinking step size, and use this multi-stage actually SGD algorithm. They can prove the convergence rate becomes 1 over t, even for the non-strong convex case. And Yongwen and I in 2021, we kind of improved the minimum maximum formulations by just actually simple observation. You can plug A, B, and alpha inside, and you expand actually the least square loss function. You can design, you can see the AUC maximization objective function can be actually formulated as a single expectations. And we propose the algorithm which can accommodate general regularization terms, which is called SPAUC. So we call this is a stochastic proximal actually SGD algorithm. And the per-iteration cost to still D, and the fast convergence can be proved even for non-convex case under some conditions. So let me quickly show you some experimental result, which is done using values on values of data set. So X coordinate is just the CPU learning time, Y coordinate is the performance of AUC score on the test data. And the blue solid line is the recent one, which is SPAUC. And these are kind of values of method which I mentioned before on one-pass AUC and online AUC maximization and faster AUC. And this method we proposed just in previous slides seems the performance faster than all other algorithms. So I have to mention here the experimental focus on the linear models here. This kind of stochastic primal dual method can be further improved by exploring exploring the data structure. So for the previous stochastic primordial method, you have a pay iteration cost, which is linearly with respect to data dimension. So for some data set is very sparse. For example, sparse high dimensional data, which is very common for actually online advertisement, for email spam filtering, these kind of applications. A common feature of this data is you have a very high dimensional input, which is X, and D can be million. But for each X, you only have very few non-zero features. So how do you explore this kind of data structure to further reduce the pay iteration cost? The main idea is also coming from the main observation for fixed W. So although auxiliary variable A, B, and alpha can be computed exactly. So, what's the main idea? The main idea is AWT, for example, at the time T, you compute the inner product of W and the implicit, right? So if you apply directly the previous stochastic primordial algorithm for AUC maximization, you still got the pay iteration cost is T, because even for each Xi has sparse features, but the summation of actually this data, maybe is not sparse. Okay, so if you directly apply stochastic primordial method, it will give you a pay iteration cost still actually is very high. So the idea is to write down actually as follows. You rewrite actually this inner product in this way, and then you replace WT plus T minus 1 by WT minus 2. And this is called lazy update, right? In the online community. And now you will see AWT minus 1 is just actually AWT minus 2 from the previous step. And the extra term is cost is WT minus 1 and inner product of XT plus 1, which is a positive example at time T. And this pay iteration cost now is reduced to K by the induction, because this is a previous actually calculation at time T minus 1. If this pay iteration cost is K, and you will see actually the cost for compute A at the time T will actually have a pay iteration cost still is K. Okay, so this lazy update tricky seems works very well. So this is show you actually some experiments which we have done. This is y-axis is AUC actually score on the test data. This is the sample size you see for the online learning setting. You will see now with the lazy update, the stochastic primordial algorithm actually performs actually very stable, converges faster than actually without the lazy update, which is consistent with other observations in the online community. And to compare CPU learning time, you will see this is the algorithm with lazy update. We propose the latter one. So y-axis is just the AUC score, x-axis the CPU learning time. So CPU learning time for this particular sparse high dimensional data application, the new algorithm will perform much faster. So roughly it can be actually 20 times faster than the previous stochastic primordial algorithms. And there's various other extensions based on these minimum maximum formulations. So for example, in this paper, further improve the convergence rate to the linear convergence rate by applying variance reduction techniques. And also recently, papers consider AUC maximization with differential privacy constraint to address how can actually design privacy preserving SGD algorithm for AUC maximizations. And again, this method focus on the minimum maximum formulations. So to summarize the stochastic primordial algorithm for AUC maximization, These studies mainly explore the structure of the least square loss function for AUC maximization. And you can decouple actually pairwise structure using the minimum maximum problem, minimum maximum formulations. And from this minimum maximum formulation, you can develop stochastic primordial algorithms, which is you only need to sample individual examples instead of pair of examples. And further, actually, improvement can be possible for example, to handle actually sparse par-dimensional data by introduce lazy updates. Having said that, all these kind of studies both focus on the linear case or the kernel method case. So thank you.
Okay, thanks to Yimin for the great talk about the old school methods and some stochastic methods for AUC maximization. So next, we're going to switch to Min Rui. He will talk about some recent works for deep AUC maximization.
Hello, everyone. This is Min Rui, and I'll talk about the section of AUC maximization in the era of AI. So the motivation of this section is that we want to maximize AUC with deep learning. So here is the motivation. We have an ImageNet challenge, which has 1,000 object classes, 1.2 million training data set, and 100,000 test data set. It's a huge data set. And we know that deep learning achieves very good classification performance, right? For example, this picture actually shows the revolution of deep learning. And actually, after AlexNet, actually the deep learning performance becomes better and better when the layers becomes deeper and deeper. For example, the GoogleNet, they get like 22 layers, right? And then for the residual net, they get 152 layers, and they get deeper and deeper, but the performance would be better and better. So the question here is that how can we maximize AUC with deep neural networks? So the current deep learning library, they usually only consider the cross entropy loss. They don't consider the optimized AUC, but AUC, as mentioned in the previous part, is a very important topic, right? And so the goal of this part is actually to have the new paradigm, so-called deep AUC maximization, or short for DAM. Actually, the workflow is the following. So we have the medical images, for example, and we have a backbone CNNs, we have classifiers, and then the model training part is completely different compared with the previous approach. So the goal is actually to provide seamless transition from maximizing classification accuracy to maximizing AUC in deep learning libraries. And then we'll show how to do that. And then we talk about some earlier works. So in Ian et al. At ICML 2003, they first uses a multi-layer perceptron for optimizing AUC by full batch gradient-based method. So basically, they need to sample a whole batch, which means that they need to go over all the data set, and they are approximating the Wilson-Mann-Wendley statistic, which is actually a statistic related to AUC. It's actually by early days AUC. And then the recent AUC optimization, as mentioned in the previous part, can be written as a minimax problem. And then there are some universal algorithms for non-convex minimax optimization, and it's very important to study that before diving into the details of deep AUC maximization. Okay, so this is the general formulation of the non-convex minimax optimization, and we have two decision variables v and alpha, and they have a joint value function fv comma alpha. And the challenge here is that the objective value function is non-convex in terms of v and concave in terms of alpha. And for example, many applications would satisfy this assumption. For example, AUC maximization, adversarial training, generative adversarial networks, etc. Distributional robust optimization, etc. And the goal usually in optimization community, people usually care about find the stationary point, which means that we consider the inner max function and we want to take the gradient in terms of V over the max function, and we want to guarantee that we can find a V such that the gradient of this function is sufficiently small and epsilon is a small threshold, is usually 0.1 or 0.01, something small. And how to achieve that? Rafik et al. At 2018, they proposed the first algorithm, a double loop algorithm, which can achieve the epsilon stationary point for non-convex minimax optimization. It's a double loop algorithm. So first is the K loop, right, the outer loop. The first, at the case stage, they actually first define a new function, fk, which is actually nothing but the original function plus some quadratic terms. And rho is actually like regression parameter, which is the positive parameter, and vk is like the anchor. And they define a new function fk, and then the inner for loop is trying to optimize the minimax problem defined by fk. So the algorithm is pretty simple. You just update the v by the stochastic gradient descent. You can see that this is actually the stochastic gradient, and c is the mini batch, is the sample, right? And for the alpha, they are doing stochastic gradient ascent with sample c as well, right? And if the function is additionally is strongly concave in terms of alpha, then there's an additional step, which is actually is like we give them give a good model v, and then they actually compute the closed form solution of argmax. So this is actually the outline of this algorithm. And they show the first asymptotic convergence rate. So in the non-convex concave case, which means that it's not strongly concave and the last line would not be executed. And then if they choose the eta k to be 1 over square root of k, and tk is actually the number of inner iterations to be order of k squared, and then they can end up with complexity of order 1 over epsilon 6. Okay, is the polynomial time complexity. And then further, if the algorithm have good properties, like actually the function is strongly concave, then if we choose the eta k to be 1 over k and tk to be k, which means that we have more aggressive step size here. And then if the function has finite sum bilinear structure, this assumption is to make sure that this argmax part can be solved efficiently. Okay. And then their algorithm have a complexity order of 1 over epsilon 4 plus n over epsilon squared. Here, the n is actually the number of summons here. So let's say usually in machine learning, we have a finite sum problem. So n is number of samples. So they have the additional complexity n over epsilon squared here. Right? This is the first non-convex minimax optimization algorithm, is a double loop algorithm. And then Yan et al. In Europe 2020, they provide a sharp analysis on the double loop algorithm on the non-convex strongly concave minimax problems. So the key idea is that they want to remove the argmax operation. Remember, in the previous algorithm in Rafik et al., they have the argmax operation, and that's the source of this complexity, n over epsilon squared. And you can see this algorithm, they are very similar. So they also have the double loop, right? And they define the fk as the original function plus quadratic, and they have the SGD for the v and the stochastic gradient ascent for the alpha, but they don't have the argmax step anymore. They use a sharp analysis to remove that, which basically means that that step is not necessary. Technically speaking, they use the duality gap analysis to get rid of that. And then they get improved the complexity from these to order of 1 over epsilon 4. So it's actually better because they removed the dependency in terms of m. Okay. And then Lin et al. At ICML 2020, they designed a single loop algorithm. Remember that in the previous two algorithms, they are all double loop, right? And their key insight is that they use the 2 time scale stochastic gradient descent ascent. So the algorithm is pretty simple, it's just a 1 loop algorithm. And then they update the v, the minimization variable, by mini batch stochastic gradient descent. And they update the dual variable alpha by mini batch stochastic gradient ascent. Right. And they have the guarantees for 2 cases. The first case is that for non-convex strongly concave case, they can choose the large mini batch. M is the mini batch size to be 1 over epsilon squared, and the number of iterations to be order of 1 over epsilon squared, right? And then they can get a complexity of 1 over epsilon 4. So this complexity matches double loop algorithm. And then in the second case, they consider a non-convex concave algorithm. And they choose M to be constant. They can allow constant mini batch in that case, but they need to run 1 over epsilon 8 iterations to make sure they can converge to the epsilon stationary point. This algorithm, although this has worse complexity, is actually a simple loop algorithm. So yeah, so if you don't need a lot of tuning, you may use this algorithm. And Bott and Blum, they consider a single loop algorithm with a slightly different update. They are using so-called alternating gradient descent ascent. So you can see that the key difference is here. Here is VT. So for the V, actually they update the parameter, right, based on the previous VT and alpha t minus 1. And then for the alpha, in the previous algorithm, they used the actually previous step, VT minus 1, to calculate their gradient. But for this alternating gradient descent ascent, they use the most recent VT here. It's like they calculate the VT and then they do the gradient calculation based on the VT. So it's actually more challenging to analyze. Yeah, and so it's actually the alternating gradient descent. And they achieve the same complexity as the gradient descent ascent with 2 time scale, as Lin et al. At SML. And they also consider a proximal variant of this algorithm, which means that it may not be gradient descent. They can allow some like regularization, like the L1 regularizer, L2 norm regularization, such that they have the closed form crossover mapping, and they can handle that case as well. Okay. And then Go et al. Is at 2021, they developed another single loop algorithm based on so-called moving average estimator. And this algorithm, they remove the requirement of large mini batch for solving non-convex strongly concave minimax problem. So the algorithm is pretty simple. They have the t iterations, and they have the momentum buffer here, MT, which is like the moving average over the historical gradient with momentum parameter beta. And then they update the V using the momentum parameter, using momentum gradient. And then they update alpha using the stochastic gradient ascent. And this line mimics the momentum people use in deep learning, or for example, SGD momentum or Adam algorithm, they use similar techniques here. And Go et al. They proved that if they choose constant mini batch size and large momentum parameter beta is actually 1 over epsilon, order of epsilon square. Epsilon is a small number here. So if beta is large, and they use this algorithm, they can show that the gradient complexity is order of 1 over epsilon 4. So this algorithm is an improvement over previous algorithm that either requires double loop or requires large mini batch size. And also this large momentum beta mimics the Adam algorithm parameter in practice. Usually SGD momentum or in Adam, people choose beta to be 0.9 or 0.99. And this is actually a theoretical explanation for that because beta is sufficiently large because epsilon is very small. Okay, there are some further other techniques, for example, variance reduction technique to further improve the convergence rate for non-convex and strongly concave minimax problem. For example, Rowe et al. And Huang et al. They can prove that the complexity can be improved from 1 over epsilon 4 to 1 over epsilon 3. The technique they are using is that they utilize that every individual function is smooth. It's like every individual function is smooth, which means that you pick any sample and the loss function is sufficiently smooth. And then they use the variance reduction technique from several ideas for minimization problem, for example, Spider from Fang et al. And the Saraf and also Storm. These techniques are actually from minimization problem, and they actually borrow the insight here and do some innovation and try to prove the variance reduction technique, and they improve the complexity to 1 over epsilon 3. Okay, so that's all for non-convex minimax optimization. And here, our focus is not only in the non-convex minimax optimization, we focus on the particular problem of stochastic deep AUC maximization. And so we need to use some structures of deep AUC maximization. It's not a simply non-convex concave minimax problem. So consider the deep AUC maximization with quadratic loss, right? Remember in the previous Yiming talk about that, right? So they have the function of f of w is actually defined on the pairwise loss. Is actually they use the quadratic surrogate to replace that. And f of w is the model deep neural network of X prime. Okay. X prime, X, Y, X prime, Y term, they are actually pairwise data. And actually using similar techniques at Yin et al., they can prove that the deep AUC maximization problem can be also written as a minimax form. And it's not mentioning that the non-convexity comes from deep neural network. Here you see that W is actually the model parameter in deep neural networks. And because deep neural network is non-convex, so this problem is non-convex in terms of W. But fortunately, it's actually strongly concave in terms of R. There are some quadratic terms there, so it's strongly concave. And Liu et al., they proved that in iClear 2020, they proved that they proposed an algorithm for the proximal primal dual stochastic gradient for solving that problem efficiently. So they first define a variable V as the W, A, and B. They concatenate all the minimization variable together. And in the stage-wise algorithm, at the S stage, the PBTSG try to implement the following line here. Okay, so this is actually the original objective value function, and they plus a quadratic term with anchor Vs here. And they want to approximately solve this problem to get the next solution. But unfortunately, this is approximately equal, which means that we cannot solve this right-hand side problem in closed form. We need to use some solver to solve this problem. And why this kind of update makes sense? Because the intuition comes from so-called fixed point iterate. Let's say the Vs is our solution, and the Vs converges to V star. Here, V star is the optimal solution. And then this kind of update, if we can make this approximately equal to be exactly equal, then this is the inequality here, which means that it will not change the solution. If we are good enough, this update will not change the solution. So the algorithm is so-called fixed point iterate. This is actually the intuition of the algorithm. The remaining part is that how can we implement the approximately equal? Right, that's the remaining problem. We want to use some structure of deep learning to accelerate the training steps of this step. And the way to accelerate training is that they leverage over-parameterization. And there is a paper by Alan Zhu, Yuanzhi Li, and Zhao Song. They show that this is in the deep learning training. The horizontal axis is number of epochs, and the vertical axis is the objective value. Is some norm, and actually they can show that during the training, the gradient norm is always the upper bound of the objective value. This is actually mimics so-called Polyak-Rogers-Stewart's PL condition for over-parameterized neural network. They proved that holds for over-parameterized neural network. And Liu et al., they actually built on this insight. They proved that the PL condition holds for AUC function like this. And basically, the phi v is actually the inner max function. They proved that the phi w minus the optimal w can be bounded by 1/2 mu times the gradient norm square. So basically, it's a very good property, which means that if we can find a point with very small gradient, it's also not far away from the optimal solution in terms of objective value. And PL condition is a weaker notion than strong convexity. Since it allows the function to be convex. So this function may be non-convex, but it actually has the PL condition holds. And by leveraging the over-parameterization, they actually, Liu and all, they propose an algorithm, the PBDSG algorithm. Similarly, they define the regularized function f of s as the previous function plus some quadratic term anchored at Vs. And then they run primal dual stochastic gradient to optimize the inner function. And the algorithm is pretty simple. They recently received one example. They run the stochastic gradient descent for V and stochastic gradient ascent for alpha. And the main innovation here is that they consider the geometrically decaying step size, eta, over stages. And recall that in the previous papers by Rafik et al., they need the polynomially decaying step size. And this is not practical. And in deep learning, people usually use exponential step size. The reason is due to the PL condition. They can use the PL condition to design the geometrically decaying step size. And then they can show that they have the 1/epsilon complexity for finding the model with epsilon optimal AUC, which means that if they want to find the model which is epsilon close, which the AUC value is the epsilon close to the optimal AUC, then they need 1/epsilon complexity. So the global guarantee is no longer only trying to find the stationary point. They can they can find the global optimal solution with this complexity order of 1 over epsilon. And there are some experiments of their paper, and they consider 3 settings. One is a very imbalanced data set on theta 100, and the second is mildly imbalanced with 71% positive data ratio, and the another is balanced data set with 15% split. And they can show that they have considered different methods. First is the red method, is actually standard SGD for optimizing cross-entropy loss. This is actually what people use in deep learning library. And the green algorithm is the PBD type algorithm, proximal gradient algorithm with polynomial decay in learning rate, which is actually the algorithm used in Rafik et al. And then the blue curve and purple curve are actually 2 variants of PBT algorithm with geometrically decaying learning rate. So this is the algorithm by Liu et al., which is specifically designed for AUC maximization. And we can see that the red curve is always the worst one, unless for the balanced data is okay. And because the red curve is not designed for maximizing AUC, they are designed to actually optimizing the cross entropy loss. And the blue curve and purple curve and the green curve, they are actually solving non-convex minimax problems, and the geometrically decaying learning rate is better than a polynomially decaying learning rate. Yuan et al. At ICCV 2021, they proposed a different margin loss, which is better than the square loss to achieve better robustness. The idea is the following. So originally, we used the square loss as the surrogate loss for AUC. Is as the following. Here, the AW is actually the score of negative data, BW is the score of positive data, and C is the margin. So the issue of the square loss is the following. So if BW is large and AW is small, then we are good enough. So the AW minus BW minus C may be a negative number, but we can still suffer some loss from the squared loss because it can be positive. So the margin-based loss proposed by Yuan et al., they are actually trying to address this issue by taking a max before taking the square. So if the AW minus BW minus C is negative, then we don't suffer any loss. So this loss is more robust than the squared loss. Let's see the following pictures. Let's see the pre-trained models. Actually, they have a clear decision boundary. It's very good. And in the AUC squared loss, if we add some easy examples here, the decision boundary is even worse. So it has adverse effect on the easy data, right? And the AUC marginal loss is better because even we add the same easy data here, the decision boundary is not bad. And also for the noisy samples, if we add some noisy samples here for the square loss, you can see that this is very sensitive. The decision boundary changes a lot. But for AUC margin loss, the decision boundary will not change. It's still basically the same as the original pre-trained data case. Okay, so this is actually the benefit of margin-based loss. And also, they show that if they replace this square loss to margin-based loss, they also have the minimax formulation. The only difference is that here the alpha is non-negative. And in the previous square loss, alpha can be any number in real life. And Yuan et al., they also proposed interesting approach for deep AUC maximization, so-called two-stage approach. The idea is the following. The stage 1 is actually to do the pre-training step. That's actually minimize the cross-entropy loss, is like here. So for the regular pre-training, they have the X-rays, they have the backbone network, they have the classifier, they have the loss, which is actually the standard training people use in deep learning library. The goal of stage 1 is actually try to learn the features of those data sets. And then the stage 2 is actually using the deep AUC maximization step, which means that once they learn all the features, and then they start to train deep AUC maximization problem. So the intuition is that the first stage is trying to find a good representation of the data. And in the second step, once we have a good representation, we can fine-tune the network to do the AUC maximization. And they show that it's actually very important for get good performance in real data sets, for example, in the medical image data classification. Okay. And then I talk about another variant, which is so-called federated deep AUC maximization, which is actually trying to train AUC with deep neural network in distributed setting or in federated learning setting. So why the federated deep AUC maximization is important? So it's actually in the real data application, for example, the hospitals, they don't want to share the data to each other hospitals because it's private data. And all the data might be very imbalanced and heterogeneous. And also communication between those agents are pretty expensive. So due to this reason, McMahon, they actually proved, they proposed concepts for federated learning. And but the federated learning is usually was actually only solving the minimization problem, like the minimizing the cross entropy loss. The question here is that how can we maximize AUC with deep neural networks in federated learning setting? So there's a naive parallel solution, which is pretty simple. So we have the minimax reformulation, as we mentioned before, and the algorithm can actually only run one step of primal dual local update before the communication happens. So here is actually 3 machines, for example, and they run one step of primal dual update and then communicate and average all the weight together. So this is actually a naive parallel solution. The issue of this solution is that it has high communication cost. For example, if you have k machines, then we have 1 over k epsilon iterations on each machine, and we have 1 over epsilon communication rounds. So when epsilon is small, then this communication round is unaffordable. We cannot afford that. So to solve this problem, Wu et al. At ICML 2020, they actually provide communication efficient distributed AUC maximization. So the idea is that instead of communicating once, they communicate multiple steps of communicate before multiple steps of primal dual local updates. So the effect is that they can reduce the communication cost. Basically, they can show that they have the linear speed up, which means that they have 1 over k epsilon iterations for finding the epsilon optimal solution, and they only need order of 1 over square root of epsilon communication rounds. So the communication round is much better because the previous one is 1 over epsilon, and this is 1 over square root of epsilon, so it's much better. So the algorithm is actually in detail is the following. Actually, they are trying to solve the minimax problem in distributed setting, and they have k machines, so every machine have a local function f of k, and actually the algorithm is actually using the reference point v0, and every step they have actually a for loop. They are running the primal dual updates, and when the t plus 1 is a mode of I, then they do communication. If t plus 1 is not the module of I, they are not a multiple of I, then they do not communicate. So it's actually nothing but multiple step of primal dual local updates. And they show some experiments showing that the first is parallel speed up, which means that they fix the I to be 16.4. They allow 16.4 step of primal dual update before communication. And they show number of machines. When number of machines becomes larger, actually the running time is actually smaller. And the second picture is actually show the effect of skewed communication. They actually have 16 machines, and when the I is not so large, they can actually improve running time. Okay, and Yuan et al. At ICML 2021. They actually consider a more challenging problem, so the federated DAM, deep AUC maximization with heterogeneous data. So in the previous Gu et al. ICML paper, they require the data to be homogeneous. But here, Yuan et al. Consider the heterogeneous data. And the key idea is that instead of running primal dual update, they actually update the primal and dual solution by a controlled variable like this. So here the GT is like the stochastic gradient, and CI is the history average gradient on ice machine, and C is actually history average gradient on all machines. So when they communicate, they can calculate those statistics CI and C, and then they do some correction over the gradient GT. And somehow this minus CI plus C, this correction term can alleviate the heterogeneity. And somehow they can show that they only need constant communication complexity to achieve the epsilon optimal solution of AUC maximization problem. And they have some experiments. It's like AUC performance. You can see that on different ImageNet data set. They can show that AUC performance would not be degraded if the number of iterations is less than 512 before communication. So they can allow at most 512 iterations of local update before the communication happens. And then the last part is the feature learning of deep AUC maximization. So there is the need is that we want to do end-to-end convolutional deep AUC maximization. So the previous work, as I mentioned, they require two-stage training. The first stage is to standard training, and then the fine-tune network to optimize the cross-entropy loss, AUC loss. And Yuan et al. Actually, 2022, they actually try to have a new paradigm. So for the end-to-end training of deep AUC maximization, the idea is the following. They propose the composite objective. They actually pretend the model is doing one step of gradient descent over the cross-entropy loss, and then they want to minimize the AUC loss here. So it's a composite function, and this, in that way, they can learn the feature and the AUC simultaneously. And they are also able to reformulate this problem to a minimax problem, and it's a composite problem. And in terms of W, so they are using the moving average estimator for the inner variable W, and for atom update for the model weights. And then they use the stochastic gradient ascent for updating the maximization variable theta here. And they can show the same conversion rate as in the standard training, but they are optimizing a more challenging objective, which is the composite objective. And they can show that their experiment is much, much better than the previous result. You can see that the CT's compositional training, they can get uniformly better result than other methods. And there are some illustration of this picture. So they consider actually the visualization of the feature learning. You can see that the baseline cross entropy from scratch, AUC from scratch, and AUC combined with cross entropy, they add them together and train them together. And CT is compositional training. And we can see that actually the data separate a lot from different categories. So it actually means that the feature learning of compositional training is better than the previous method. Okay, so we have a summary here. We do the full batch method for optimizing AUC with neural network. We have introduced non-convex concave minimax optimization problem. We consider how to leverage over parameterization as a non-convex concave minimax problem. We consider two distributed algorithms, and we also consider feature learning of deep AUC maximization. And thank you. Let's have a break for 15 minutes. And if you have any questions, feel free to ask. Thank you.
Thanks, Binri, for talking about deep AUC maximization. So if you have any questions, the two speakers are online. Feel free to ask them. Miri, did you hear that?
No, I don't hear that. It's not very clear to me.
So, AUC optimization, what you're speaking about, is for a binary classification system?
Yes, that's a question. I heard about the binary classification, right?
So the question is, can it be extended to a multi-class setting?
That's a good question. We currently assume binary classification for, it makes the theory to be easy to analyze and it's easy to extend that between a multi-class. So in the multi-class, you can just use the one versus all approach, and then you can construct the pairs of AUC, and you can use the easily extend that to multiple class classification setting. Yeah.
What? Yeah, same guarantee. Yes. Yeah. And also in our library, we also implement the for the multi-label setting, multi-task setting. If you have multi-task, so basically for multi-class, you can consider the multiple tasks. Yeah. So we are averaging over classes. Yeah. Any other questions? Also, we can have a question from the online audience. Okay, and also feel free to take a break. We're going to start at the 10:30. will integrate them.
I see that.
Yeah, we do that. We do. Oh, I think no, this is first the nearest coordination. I'm also going to that's a it is. It is. Yeah, so that's probably because you can actually follow our tutorial. So wait, so let me show you. So we have this website, leaveauc.org. So this is our library website /CVPR 2022. We have this tutorial website. At the end here, at the bottom here, you have a link to this survey. So basically, all the works that mentioned by Yimin, by Minri, you will see the citation in that survey paper. Yeah. Okay, to keep us on track, let's get started with the third part. So for the third part, we're going to go beyond the standard AUC maximization. First, Harry will talk about partial AUC maximization, and then I will talk about average precision maximization. Okay, so I will play the talk by Harry.
Hello everyone, my name is Hari Narasimhan, and I will be covering the next 30 minutes of the tutorial. The focus of this portion of the tutorial would be on partial AUC maximization. The first half of the tutorial covered maximization of the AUC ROC metric. We now move to metrics that go well beyond the standard AUC metric. And one such example is the partial AUC evaluation metric. In many real-world applications, one is often interested in performance in a select portion of the ROC. For example, in many ranking tasks, one is interested in performance on the top few ranked instances. Similarly, in many biometric screening applications, one often desires classifiers that have a very low false positive rate. Both these requirements boil down to measuring performance in the initial portion of the ROC curve, with the false positive rate restricted to a certain upper limit. Similarly, in many medical diagnostic applications, there are often restrictions on the acceptable range of false positive rates. In this case, one may again want to measure performance in terms of the AUC, but with the AUC restricted to a range of false positive rates. In some other applications, a medical professional may prescribe a limit on both the true positive rate, the minimum allowed true positive rate, and the maximum allowed false positive rate. In this case, one would want to measure the performance in terms of the AUC, but restricted to a certain range of true positive rates and a certain range of false positive rates. So our goal in this portion of the talk would be to maximize the partial AUC objective. Before doing so, I'd like to reintroduce some notations to simplify writing out this partial AUC evaluation metric. We'll denote positive examples using X plus and negative examples using X minus. Our goal is to learn a scoring function which can be used to either rank objects, if you're interested in a ranking application, or to build a classifier by applying a threshold on the scoring function. Let's quickly go through a toy example to recap how one generates a ROC curve, and this would give us some intuition for some of the methods that we'll cover later on in the talk. So consider a toy example with 6 positive instances denoted in blue and 6 negative instances denoted in red. A score is associated with each instance, and the instances are ranked in descending order of their scores. To plot the ROC curve for this assignment of scores, we'd apply a threshold on the scoring function and trace out the true positive and false positive counts as we move down the threshold from the higher score to the lower score. So when we apply a threshold after the first positive instance, notice that we go up 1 position on the true positive axis. The true positive count increases by 1. When we move the threshold down a negative instance, the false positive count increases by 1, and therefore we go to the right on the false positive. And as you can see, as we trace out the ROC curve, every time we move past a positive example, we move up 1 position on the true positive axis, and every time we move past a negative example, we move to the right by 1 position. As we have already seen, the full AUC, which is the area under the full ROC curve, can be written in terms of a pairwise expression, where you look at all pairs of positive and negative examples and calculate the fraction of pairs where the positives rank above the negative. As noted early on, the partial AUC metric also has a similar form. For example, if you're interested in the partial AUC with a false positive rate restricted to the initial portion of the curve, we can write out this metric as a pairwise expression similar to the full AUC, except that we only look at a subset of pairs. In this case, we'll be including only the top ranked negative examples in the ranked list because we are restricting the false positive rate. And remember that moving the threshold past the negative example takes us to the right on the false positive axis. Similarly, if you are interested in the partial AUC with a lower bound on the true positive rate, in this case, we'll be looking at the bottom ranked positives in formulating the pairs. This is because when moving the threshold past the positive example, we move up one position on the true positive axis. Now, given that we have built some intuition, let's use this intuition to recap what the estimators were for the partial AUC. We use I within square brackets to denote the positive example at the bottom ith rank position among the ranking of positives. We use square brackets J to denote a negative example in the top jth position in the ranking of negatives. We use I alpha to denote the maximum rank for the positives. And we use J alpha and J beta to denote the range of ranks allowed for the negatives. The one-way partial AUC metric, which we have seen restricts the false positive rates to an alpha beta range, can be written using the pairwise estimator shown, where we look at all positives but only look at negatives ranked in positions J alpha to J beta. The two-way partial AUC metric, which restricts both the false positive rates and the true positive rates, again as a pairwise estimator shown on the slide, where we look at positives ranked in positions 1 to J alpha from the bottom and negatives ranked in positions 1 to J beta from the top, and formulate pairs using the subset of positives and negatives. The main challenge, of course, in working with these evaluation metrics is in being able to handle this ranking of positive and negative examples. Over the last few years, over the last 1 decade, multiple methods have been proposed in optimizing the partial AUC metric. And each of these methods have a particular way of handling the ranking of positives and negatives. The remainder of the talk would cover some of these techniques. We'll start with some initial work on the partial AUC maximization problem, which started around a decade ago, at least as far as the ML community is concerned. We'll then move to some of the more recent approaches in the last 5 years, which have improved upon the prior methods and also come up with new innovative ways of optimizing partial AUC. And finally, we'll end with some of the state-of-the-art algorithms which specifically make use of some of the recent advances in non-convex optimization when it comes to training deep neural networks. So some of the initial work on partial AUC maximization considered the one-way partial AUC metric, where we restrict the false positive rates to a certain range. The initial goal was to come up with a surrogate objective for this metric, and these works mainly focused on linear models and in some cases kernel-based models. Now, one simple approach to constructing a surrogate objective for partial AUC is to simply replace the indicator functions in the estimator with a convex surrogate loss. Now, this simple approach turns out to be quite effective, at least in one particular special case, where you only have an upper limit on the false positive rate and not a lower limit. So when you restrict the false positive rates to a 0 beta range, then it turns out that this simple surrogate objective, where we just replace the indicators with a convex loss, turns out to be over-convex in the model parameters. Therefore, one can apply standard convex optimization solvers based on gradient descent to optimize this objective. In fact, computing gradients for this objective is also very straightforward. All one needs to do is compute a sorting of the negative examples, take the top rank negatives, and compute the average gradient of the loss restricted to only those negatives. Now, this simple approach of simply replacing the indicators with a with convex laws and apply gradient descent. Doesn't quite work out well for the more general definition of the partial AUC. So if you're interested in the partial AUC with the false positive rates restricted to a general alpha beta range, then this simple trick doesn't work. In this case, one approach could be to write the partial AUC list as a difference of two terms. One being the partial AUC loss in the 0 beta range, the other being the partial AUC loss in the 0 alpha range. Now, each of these surrogates we know are convex in the model parameters, assuming a linear or kernel model. And now what we end up with is an objective, which is the difference of two convex functions. Now, the nice thing about this objective is that there's a vast body of work on optimizing difference of convex functions. And one of these works on partial AUC maximization adopts a popular algorithm available for difference of convex optimization. Now, the strategy they use is to convexify the objective by linearizing the second term in the objective. The negative partial AUC term in the objective is the term that gets linearized. So the idea here would be to linearize the second term and optimize this relaxed approximation of the partial AUC metric. Now, the algorithm that they propose does this over multiple iterations. But in each iteration, you linearize the objective, minimize the objective, and carry on over multiple terms. Interestingly, there's also been some work on coming up with convex relaxations to this general one-way partial AUC estimator. And these are based on structural SVMs. And this approach has also shown to be effective on some medical diagnostic tests. Now, following these initial works on maximizing one-way partial AUC, there were several follow-up papers with applications in cancer therapy, ML modeling for cancer therapy, and also in computer vision for tasks like pedestrian crossing detection. Apologies. There has also been work on the algorithmic front on scaling up some of these prior methods using stochastic and online optimization, and also in extending these methods to more complex structure prediction settings. So far, we've covered some of the earlier works on partial AUC maximization, but the focus was largely on the one-way partial AUC. We saw that when we only had an upper bound on the false positive rates, we could come up with a straightforward convex surrogate. And for the more general partial AUC definition, we could come up with a difference of convex optimization formulation. Now let's move on to some of the more recent work, which have explored alternate ways to optimize partial AUC, and also sought to improve upon some of these prior works. So one notable innovation in the last few years has been the use of constrained optimization for maximizing common evaluation metrics. The idea here is that rather than trying to come up with a surrogate objective for the metric that we care about, why not directly try to compute the metric from first principles? For example, when it comes to the partial AUC metric, the constrained optimization formulation directly seeks to compute the area under the curve using a standard Riemann approximation. Now, what this would amount to do would be to divide the range of false positive rates that one is interested in into a number of bins and associate a threshold with each bin. One then formulates a constrained optimization problem where each of these thresholds are constrained to satisfy the respective false positive rates. And the objective is to maximize the sum of the two positive rates at these thresholds. Now, in order to solve this constrained optimization problem, one can then replace the true positive and false positive rates in this problem formulation with surrogate objectives, surrogate relaxations, and then use standard constrained optimization solvers to solve the resulting optimization problem. For example, one could take a Lagrangian style approach where you formulate the Lagrangian and solve the Lagrangian optimization problem. In fact, there's a open source library out there in TensorFlow available for solving constraint optimization problems of this form and train neural networks by enforcing these constraints. So this was one approach that came up for optimizing partial AUC. In parallel, there's also been some interest in looking at the more general two-way partial AUC method. So for all the methods we've seen have focused on the one-way partial AUC. In the case of the two-way partial AUC, one would restrict both the true positive rates and the false positive rates to an allowed range. In this case, one could again look at the pairwise estimator for this method and simply replace the indicators with a surrogate loss. But of course, the challenge is that one now needs to deal with both the ranking of the positives and the ranking of the negatives. For simplicity, I'll be showing all objectives using a linear model, but the methods I'll be describing from now on also apply to nonlinear modelings and ring of nonlinear modeling. Now, one simple idea that has been tried out to optimize this surrogate for the two-way partial AUC method is heuristic mini-batching, where one simply ranks the positive and negative examples in each mini-batch, computes the top ranked, identifies the top ranked negative examples and the bottom ranked positive examples, and computes gradients on just a subset of top ranked negatives and bottom ranked positives in each mini-batch. So this is a very simple approach. However, it turns out that this simple heuristic mini-batching approach does not come with convergence guarantees. So a recent paper sought to come up with a slightly more principled approach for optimizing the two-way partial AUC metric. This is one of the first few works that focused on the two-way partial AUC metric. And they take an alternate approach, where rather than explicitly ranking the positives and negatives, they proposed maintaining soft approximations to the rank. This was work by Yang et al. Recently in ICML 2021, and their proposal is to use a weighted pairwise surrogate, where you have a weight associated with each pair of positive and negative examples. Now the weights are chosen to maintain a soft approximation to the ranking. In particular, the weights depend on the scores for the pair of positives and negatives, and the weights are chosen to emphasize better performance on the higher ranked negatives and the lower ranked positives. Now, in the paper, the authors propose different parametric forms for the weighting function and show that by tuning the parameters of the weighting function, one can optimize performance in any desired range of false positive and true positive weights. Okay, so we've broadly covered three different recent approaches for partial AUC maximization. One was based on constraint optimization, which was mainly focused on one-way partial AUC. Then we saw that we could apply a heuristic mini-batching approach, which did not come with theoretical guarantees, and a slightly more principled approach based on weighting the pairwise surrogate loss. And the latter two approaches apply to the two-way partial AUC and in turn also to the one-way partial AUC method. So I'll close by highlighting some very recent work in the last 1 year that are mainly focused on training of deep learning models and make use of some of the recent advances in non-convex optimization. So I'll start off with this recent paper that proposes an improvement to prior methods for the one-way partial AUC method. Now remember that one of the earlier works on optimizing one-way partial AUC formulated the objective as a difference of two convex functions. And more specifically, the idea was to write out the partial AUC objective as the difference of the loss in the 0 beta range and the loss in the 0 alpha range. However, the algorithm that they proposed for the difference of convex optimization only has asymptotic convergence guarantees. The reason for this is that both the components in the objective, the difference of convex objective, are non-smooth in the model parameters. Note that each of these components involve a ranking of negatives and therefore they're non-smooth. And as a result, the optimization algorithm that was earlier proposed does not have, has only asymptotic convergence. So the recent manuscript by Yao et al. Proposed an improved stochastic algorithm for solving the same difference of convex optimization problem. The key idea here is to apply a smoothing technique to compute smooth approximations to both the components in the objective. And then they propose a form of gradient descent for optimizing the smooth objective. Interestingly, the gradients here are computed approximately by simply computing a gradient for the first term and a gradient for the second term and computing a difference of these gradients. And the authors are able to show that this approximate form of gradient descent on the smooth objective has non-asymptotic convergence rates. In fact, in addition to showing theoretical guarantees, the authors also show improvements on experimental data sets. So here are some experiments on a chest radiography data set where the authors show that their stochastic, their difference of convex algorithm is able to do a better job of optimizing partial AUC compared to two of the earlier works. One is the SVM style optimization, and the other is the plain vanilla difference of convex algorithm. So the goal here is to optimize the one-way partial AUC metric, where there's a restriction of a lower limit of 0.05 on the false positive rates and an upper limit of 0.5 on the false positive. The right plot here shows the ROC curves for different methods. And one can see that the stochastic DC algorithm does a better job of optimizing the area under the curve in the range of interest, in the false positive rates of interest, which is from 0.05 to 0. Okay. Another recent paper in ICML this year explores alternate formulations for both the one-way and two-way partial AUC method. Now, the main idea in this paper is to use soft approximations to the ranking of negatives and positives. And more specifically, the authors take a robust optimization formulation. So let's look at the formulation for the one-way partial AUC first. And in this case, they consider a special case of one-way partial AUC where you have an upper bound on the false positive. So in their formulation, for each positive example, they associate a probability distribution over the negatives. They weight the negative losses with the distribution weights and maximize over this distribution. Now, the objective additionally includes a divergence term that measures the distance of the distribution we maximize over and the uniform distribution over all negatives. So for each positive example, you have this robust loss formulation where you have a maximization of a distribution over the negative examples. It turns out the different choices of the divergence term in objective leads to different approximations to the partial AUC method. The final objective that they optimize turns out to be a simple average of each of these robust losses on the positive examples. So one can compute a loss over the negatives with a divergence term in the objective, and one then averages these losses over the positive examples. And this is the objective that they optimize. The authors describe how this resulting objective looks like for different choices of the divergence term. For example, when the divergence term happens to be the K divergence, they get back a soft estimate of the partial AUC risk. In this case, they show that the objective is smooth under some mild assumptions, and they propose a stochastic algorithm for optimizing the smooth objective. When the divergence function happens to be the CVPR divergence, which is the conditional value at this divergence, here it turns out that you get back an exact estimate for the partial AUC risk. In this case, they show that the objective is weakly convex in the model parameters and propose a stochastic algorithm for optimizing this weakly convex objective. Now this was for the one-way partial AUC metric. Interestingly, the authors also extend their robust optimization formulation to the two-way partial AUC metric. In this case, they maintain a distribution over both the positives and the negative examples. So for each positive, as before, they maintain a distribution over the negatives, and in the objective, they maximize over the distribution with an additional divergence term included. The final objective maintains a distribution over the positive losses and maximizes over that distribution and has a divergence term again, computing the distance between that distribution and the uniform distribution over all positives. So we have two distributions here. For each positive, we have a distribution over the negatives, and a divergence term there measures the distance between that distribution and the uniform distribution over negatives. And then you have the final objective, a maximization over distribution over positives. Again, different choices of the divergence function leads to different estimators for the partial AUC risk. When the divergence term is chosen to be the KL divergence, you end up with a soft estimator for the partial AUC risk. In this case, it turns out that the optimization objective is actually a composite, a nested objective with 3 levels of nesting. The inner term computes a soft approximation to the top negative losses for each positive example. And the outer term computes a soft approximation to the rank positive losses. Now, because this is a composite nested objective, the authors adapt a prior stochastic algorithm proposed for such composite objectives, right? And they're able to show convergence guarantees for the stochastic algorithm. They additionally also show that this robust optimization algorithm works well in practice on several image and molecular classification datasets. They show that their proposed approach performs better than 2 prior approaches, one being the ad hoc weighting approach, the other being the heuristic manufacturing approach that we just saw earlier in the slides. The goal here is to maximize two-way partial asymmetry, that you have a lower limit of 0.6 on the true positive rate, and the upper limit of 0.4 on the false positive rate. In the plots, one can see the partial AUC values for different algorithms. As we increase the number of training epochs, the robust optimization algorithm shown in blue can be seen to achieve a higher partial AUC value early on in the course of optimization compared to the other methods. So with this, we have come to the end of this portion of the talk on partial AUC maximization. Let me close with a brief recap. We started with some earlier works on partial AUC maximization, but the focus was on the one-way partial AUC metric. These works provided convex surrogate for special case, and more generally, they looked at the difference of convex formulation. The more recent works have looked at alternate constraint optimization-based approaches for maximizing the one-way partial AUC. And we also saw some initial work on the two-way partial AUC maximization problem using pairwise weighting. Finally, we saw that in the last 1 year, there's been a couple of works based on recent advances in non-convex optimization. These include both an improved difference of convex algorithm and also algorithms based on robust optimization, which have shown to improve upon the prior methods available for partial AUC maximization. So with this, let me hand over the talk back to Tianbo. Thanks everyone for listening.
Okay, thank you, Harry, for the nice talk about partial AUC. So in the remaining hour, we're going to show this thing. So I'm going to talk about AP maximization. I think this part is probably more interesting to the researchers in computer vision community. And also, we'll talk about a library that we developed for deep AUC maximization. Okay, so let's recall the definition of AP average precision, right? So for a set of examples, right? So we need to sort their scores, rank their scores right in the descending order, right? And then for each positive example, we can compute a precision, right? So basically, for each positive example, we use its score as a threshold, right? So above the threshold, everything predicted as positive. Below that, everything predicted as negative, and then you can compute the precision. And precision basically is how many examples above that threshold are indeed positive and divided by the number of examples above that threshold. Right? So for each positive example, you can get a precision value, and then you can average over all positive examples. You get the average precision. Right? So we have two scenarios here. In the left scenario, it's not perfect. The average precision value is 0.7. In the right scenario here, we have a perfect ranking. The positive examples are ranked above negative samples. So the average precision value is 1. So you can see that in order to compute AP, right, so it involves ranking, by ordering of examples. Ranking is actually non-differentiable, right? And also the AP score itself is non-decomposable, not even pairs, right? So this is not like the AUC score, which is decomposable over pairs, right? By using square loss AUC, we can transfer into min-max objective, which can be even decomposable of individual data, right? But this is not the case for this AP score, so which make more challenging than AUC maximization. So next, I'm going to talk about two categories of approaches. One is a deterministic approach, another category is stochastic approaches. One thing I want to mention that except this AP maximization or other materials, the talks given by other three speakers, we have a survey paper, right? So you will see you can find the related work in the survey paper. But for this part, AP maximization, we didn't include that in the survey paper. So, but for the papers we're going to talk about, I already directly post the link here. You can follow the link in the slides, and we will put the slides on our website. And also, I want to point out that, I mean, AP maximization, there is a huge amount of work about this AP maximization. We cannot cover all of them. We just choose the most representative one and talk about them, and hopefully we'll cover them in the future work. Okay. So the work by Matt Zeller in 2005, they consider optimizing average precision by learning a linear scoring function, right? And they formulate the optimization problem as a constraint optimization problem with a constraint on the simplex. So the decision variable is on the simplex. And then they employ coordinate ascent approach, okay, to optimize the objective with line search. So basically, every iteration, they just optimize one dimension of the decision variable with a line search, right? So apparently, this type of approach has very high complexity because of line search for this coordinate descent approach. And then in 2007, Realtime proposed SVM type of approach for AP maximization. So this is inspired by the structured SVM that Amy has talked about, that Harry has talked about, right? Structured SVM, which is basically to optimize a convex upper bound of AP loss. Again, this work focused on learning a linear prediction function, right? They employ cutting plane method to solve the constraint optimization. In the cutting plane method, every iteration, they need to solve a subproblem. So basically, to find the most violated constraints, they need to solve a subproblem, which is referred to as loss augmented inference subproblem here. So this loss augmented inference subproblem is a maximization problem. So here, the L, capital L, is a AP loss. Okay, so that measures the loss of the ranking R versus the optimal ranking R star. So R star is an optimal ranking induced by the ground truth label, right? And L is just the AP loss of this ranking R. And the second term, W transpose the psi is the joint feature mapping. So basically, W transpose psi is the scoring function of the ranking R. So basically, this term measures the consistency between the ranking R and the prediction score. Okay, so every iteration of the cutting plane method, they need to solve this loss augmented inference And then they propose a method to solve this problem exactly. And for solving this subproblem, they need a complexity or quadratic complexity n plus times n minus plus n log n. N log n is the complexity for sorting the scores, n plus n minus is to comparing all the positive negative pairs. And you can see that it also has high complexity for big data because it's a quadratic complexity. And then in 2008, Qing et al. Proposed approximate AP for optimizing mean average position and also top K mean average position. So they formulate average position in terms of ranking function. So basically ranking function here R takes the data as input and output the rank for this example. So basically compare, just count how many examples whose score is larger than the X score, right? So you can see that the R function is non-differentiable because indicator function. So they use some smooth surrogate function to approximate the indicator function. For example, they use sigmoid to approximate that. And also, they also approximate another non-smooth function, truncation function, that compare the rank of two examples by the sigmoid function. And then they use gradient descent to optimize the resulting smooth version. And but this type of algorithm still has high complexity, right? Per iteration complexity is n plus times n, right? And then in 2014, Mohan Patra et al. Proposed some techniques to speed up the structure SVM approach for AP maximization. And then they realized that the bottleneck lies at solving this loss augmented inference, right? So as I said before, in Weir et al.'s approach, the complexity is n plus times n minus plus n log n. And they realized that there is some special structure they can leverage to speed up the computation for solving this subproblem, right? So basically they can reduce the complexity to n plus square plus n minus times log n plus, right? So this is better than this n plus times n minus in the previous work, especially when the number of positive examples is much less than the number of negative examples. And also they propose another heuristic approach by using two-stage approach. So basically they run standard SVM and use that to select some difficult examples. And in the second stage, they just focus on optimizing AP loss based on the difficult examples. Right? But still, this type of approach still has, we still need to go through all examples every iteration, right? So it's also not very applicable to deep learning. Song et al. At the 2016, they proposed a different approach. They consider direct loss minimization. So basically, the objective is just the AP loss, right? So L here is the AP loss that compare the predicted ranking RW and the optimal ranking R star, right? To compute the AP loss. So the predicted ranking RW is by maximizing a scoring function. So basically, as I said, the scoring function is measure the consistency between a ranking R and the prediction score, right? So prediction score can induce a ranking RW, right? But the challenging for this problem is that how do we compute the gradient of the loss in terms of model parameter W, right? So their contribution is to derive a general loss gradient theory for this problem following a previous work by McLester. Okay, so basically this general loss gradient theorem shows that, okay, so the gradient of the objective in terms of the model parameter W can be represented as a difference of two gradients, okay? And also for the two gradients part, we need to first do the forward propagation for solving two loss augmented inferences, right? And then by having that, we need to do back propagation based on the scoring function. All right, and also the proposed approach, dynamic programming approach for solving loss augmented inference for learning a deep neural network. Okay, but this type of approach still suffers the high complexity, the same complexity of solving loss augmented inference. So basically, still have the quadratic complexity n plus times n minus every iteration. Okay, and starting from 2017, we have seen some work trying to use stochastic methods, mini-batch-based stochastic method for optimizing AP. And in 2017, Eban et al., they proposed a constraint optimization. So this is very similar to the one that Harry has just talked about for partial AUC maximization. So in this paper, they express recall at a certain precision value of the constraint optimization problem, right? And then they consider all possible values of the precision, but considering all possible value of the precision is not very interesting because that has a lot of constraints. So they discretize all the possible precision values into a finite number, okay, and they have finite number of constraints, and then in the objective just sum over the weighted recall values. And then they use Lagrangian theory to convert the constraint problem into min-max optimization problem. So the pros of this approach is that the min-max objective becomes decomposable over individual data, and then standard min-max stochastic min-max algorithm can be used to solve the min-max problem. But the cons is that there is no conversion guarantee in terms of the original AP maximization problem. And in 2019, Kako et al. Proposed another approach called fast AP. They use some key techniques, right? So first, they use variable transformation. They express AP as a parametric function of the distance from the query to the items, right? So in the information retrieval setting, and then you utilize the smooth quantization, right? Instead of hard quantization to compute a smooth AP version, which allows them to do the backpropagation. And then to avoid processing all examples at each iteration, they just use the mini batch examples. Every iteration sample mini batch and then calculate approximate AP and its gradient based on the mini batch. So the cause is that there's no convergence guarantee of using mini batch examples, and also their experiments show that it's very, very sensitive to the batch size. So if you have small batch size, you may have suffer from large optimization error, as shown in the right figure here. And in 2020, Bottlenecks et al. Proposed another approach called the Rainbow. So basically, this approach is based on black box differentiation of rank-based function. So this is inspired by our earlier work that computes a gradient of a loss function in terms of those combinatorial objects. So basically here they directly consider optimizing the AP loss, which is denoted by L here. Remember that the AP loss depends on the rank, right? So you have a score, and the score induces rank R. So that R is used to compute the AP loss, right? So the question is, how do we compute the gradient of the loss in terms of score S? So if you have that, and then use the chain rule, we can compute the gradient of L in terms of the model parameter W, right? So the derivative theorem showing that the gradient of loss in terms of score S can be represented as a difference between the two ranks, RS. RS means the rank induced by score S. RS lambda is the rank induced by another score S lambda, and S lambda is computed by a gradient ascent according to gradient of the loss L in terms of rank R. Right. So all of these computations can be computed in the deep learning framework by auto differentiation, and also they try to avoid using all examples to compute the gradient to update the model because that is too expensive. But they also realize that using mini batch may also suffer some large error. So they propose to use a memory to store some scores that has been computed in past iterations, and use those scores to compute the loss and that helps to mitigate the mini batch error. But again, there is no guarantee of convergence. And in the same year, Brown et al. Proposed another approach called smooth AP. So this smooth AP uses similar techniques as approximate AP. So basically, they use smooth surrogate as a rank for the ranking function, right? And express AP as a function of the ranking function. And then the function becomes a smooth function, and then use mini batch examples to compute approximate AP and also the gradient AP. But again, there is no guarantee of convergence using mini batch samples, and also experiments show it could be sensitive to the batch size. Okay, to address these issues, these previous approaches, in particular the sensitivity to the mini batch size, okay, in our recent work by Chi et al., okay, by Chi et al., so we propose a new algorithm called SOUP, okay, called SOUP. So this algorithm, we optimize a similar objective as approximate AP, as smooth as AP. So basically, we express AP as a smooth function, as a function of ranking function, and use a smooth surrogate to approximate the ranking function. But novelty here is that we formulate the precision as a compositional function, and then we propose an algorithm for stochastic algorithm for solving the novel compositional optimization problem. So the pros of this approach is that it is the first algorithm with a convergence guarantee, right? And we do not depend on the batch size. So the algorithm is guaranteed to converge with any batch size. So it's not sensitive to the batch size. Okay, so let me give you some more details about this approach. So remember, in the AP, we need to compute the precision for each positive data xi, right? So we use a score of xi as a threshold to compute the precision value. So basically, the precision value here, the denominator is to count how many examples in the positive set the score is larger than the score of xi. Right? But instead of using the indicator function I, we use a smooth surrogate loss L, right? So the denominator here is to count how many examples whose score are larger than score of xi among all examples, right? So this actually gives an approximation of the precision value. Okay, and then we introduce a mapping called the GIW. Okay, GIW is a mapping that depends on individual data xi. So GIW has two components. The first component, GIW1, denotes the numerator here, and GIW2 denotes denominator here. Okay, and then we introduce another function, a simple function h. So h take the g as input, and the output is just take the first coordinate of g divided by second coordinate of g and multiply by -1. Okay, and then the precision, right? So the precision of xi can be formulated as a compositional function h of GIW. Okay, and then average over all the positive examples. So we refer to this problem as finite sum coupled compositional optimization. So this optimization problem is very, very different from the traditional empirical risk minimization, right? Because in this each individual term, GIW not only involves each data xi, but also involves other examples. So if you look at this formulation here, GIW actually depends on many other examples, depend on all the data. So that makes it very different from traditional empirical risk minimization. So if we simply apply existing stochastic algorithms like SGD, like momentum, like ADA to solve this problem, we cannot guarantee convergence. So that is actually the problem of the previous work. Simply use mini batch to calculate the precision, and their approach will suffer some large optimization error. Okay, so let's talk about the key idea of this algorithm soup. So note that the key is to compute an estimator of the full gradient, right? So in order to compute the full gradient, we need to compute the gradient of h, the out function h at the inner function GIWT at the tth iteration, right? Remember that GIWT depends on all examples. So we cannot compute GIWT exactly, efficiently, right? We don't want to process all examples. But we can compute an unbiased estimator of GIWT denoted by GIHWT. So this can be simply done by sampling some mini batch of examples and calculate unbiased estimation. But we cannot simply use GIHWT within the function h to compute the gradient estimator. The reason is that because the h function is nonlinear. So the whole estimator here is a biased estimator. Okay, so the variance of this estimator will depend on the batch size in computing the GIHWT. So if your batch size is smaller, you will have large variance, so you will have large optimization error. To address this issue, we propose to use a biased but variance reduced estimator denoted by UIT here. Okay, and UIT is simply updated by this formula, right? So at this iteration for the sampled data, xi in B plus means we only consider the sampled positive data. We first compute unbiased estimator GIHWT and combine that with the previous value of the estimator UIT minus 1. So the beta here is value between 0 and 1 is hyperparameter, right? So intuition here is that when t increases, WT is WT minus 1 getting closer to WT, and the previous value of the estimator UIT minus 1 will be very useful to estimate GIWT. As a result, UIT will have a variance reduced property, so we don't need large batch size to guarantee convergence. And then with the gradient of H at UIT, right? So we can use that to compute a gradient estimator of the full gradient of the original objective, and then we can update the border parameter by SGD style, by Adam style, by momentum style. Okay, so these are some experiments shown in the T et al. Paper. So here we consider the experiments for learning for optimizing graph neural networks on molecular property prediction tasks, right? So depending on the imbalance ratio proportion positive examples, we could have dramatic improvement from 2% to 33% improvement for learning the graph neural networks. And here we compare different baselines, including traditional method for optimizing cross entropy loss, for optimizing focal loss, class balance C loss, and AUC loss, and also different AP maximization method, including smooth AP, fast AP, and min-max AP. And also we did some experiments, ablation studies showing that our approach is not sensitive to the batch size, and compared to the existing approach for optimizing AP, we converge faster and also converge to better solution. And recently we also further improved the algorithm and the convergence and the theory for the SOUP algorithm. In the AS search paper, we proposed another algorithm called MOPE. We basically use momentum Adam style update, showing that it has a faster convergence. And in the recent ISML paper, we prove even faster convergence, showing that the convergence can be accelerated by using mini batch examples. And we also show that by sampling the same number of positive or the same number of negative examples, we could have faster convergence. Okay, and experiment also shows that, you know, with this new methods, new algorithm SOAPs, that is better than the previous variants. Okay, to summarize what we have talked about here. So we talk about direct loss optimization approach, which is to directly optimize the AP loss, right? But the key challenge is how do we derive the gradients of the loss in terms of the model parameter, right? And the second category is to optimize convex surrogate upper bounds of the AP loss following the structure SVM framework. We have SVM AP and also some techniques to speed up the computation. The third category is to optimize the smooth approximation of the AP loss, right? So we have approximate AP, smooth AP, and our recent state-of-the-art algorithm for solving this smooth approximation with convergence guarantee. Last category is transform and optimize, so they can transform the problem into a different, for example, constraint optimization, and solve the constraint optimization by some algorithms. Okay, so that is about AP maximization. So next, I'm going to introduce you a library that we recently developed, and also mention some applications that we have achieved great success with this library. So this library is called the Leap AUC library. It is a deep learning library for X risk optimization. So originally, we developed this library for optimizing AUC, including AURC and AUPRC and AP. But recently, we extend the scope of this library by including a big family of objectives of measures, which we call it X risk. So we have websites at the leapauc.org, and we also have a GitHub address here. You can follow this link actually on the website. Okay, so some key feature about this library. So it is easy to install, right? So it's built on the PyTorch platform, right? So since PyTorch is very, very popular in the community, so we build on the PyTorch. So it's easy to install. You just type this line, pip install lib AUC, you can install the library. Second, it has broad applications, right? So you can choose your favorite network. So you can define your own network structure. So our library provides the algorithm, provide the optimization algorithm to optimize a variety of risk measures. Okay, so we consider a family of risks called X risk. So that is beyond the AUC we just talked about. But the X risk here have four categories right now. The first category is the area and the curves. That includes the one we just talked about, including AURC, AUPRC, and the partial AURC. But also includes some other measures, interesting measures. So second category is the ranking measures. So we have, list-wise losses, right? So for learning to rank problems, we have mean average position, we have normalized discounted cumulative gain, and DCG. Okay, and also we have the third category with the performance at the top that includes the top K version of the mean average position and the top K version of the NDCG. And also we have a recall at the top K positions and the precision at a certain recall level. And the last category is probably very interesting here is that it includes a family of contrastive objectives that have been used by recent self-supervised learning methods. So that includes SimClear, that includes Clip. Okay, so the problem with existing approach such as SimClear or Clip is that they rely on very large batch size because the optimization does not do very well. So they have to use very, very large batch size. So one way to address this large batch size is using the MoCo framework, right? Using large memory bank to address that. But our approach get rid of large batch size, also get rid of the large memory bank. Okay, by designing a more efficient and more rigorous algorithm, optimization algorithm for solving these contrastive objectives. Okay, so basically we implement efficient state-of-the-art algorithms for optimizing a family of objectives or measures, and also some of these solutions have been used to win several competitions that I will talk about in the next few slides. And also for each objective here, we provide hands-on tutorial on our GitHub. Okay, so next I'm going to talk about some applications that this library has achieved great success. So first is about the Stanford Checkspread competition. So this is the competition organized by Professor Andrew Ng's machine learning group at Stanford. So the problem here is to detect lung-related diseases based on X-ray images. Okay, so they have collected about more than 200K images, X-ray images, chest X-ray images from Stanford Hospital, and label them. Okay, so they launched this competition in the January of 2019. So we entered this competition at end of May 2020 and then at end of August 2020. Our deep AUC maximization method achieved the first place and is still the first place at the current point. So we are the best in terms, not only in terms of AUC score, but also in terms of another metric, which is shown in the last column here, which shows that our model is better than 2.8 radiologists out of 3. Okay, so they employ 3 experienced radiologists to label some testing data and then compare the AI model solution with a radiologist prediction, right? So our model beat 2.8 radiologists out of 3. And also we have applied this library to other medical image classification tasks that includes, detecting melanoma, which is skin cancer, detecting breast cancer based on mammogram images, and detecting tumor based on microscopic images. And then we have improvements we compare to the traditional deep learning approach by optimizing causal entropy loss. We have improvement from 1% to 5% depending on the imbalance ratio, which is the proportion of positive examples. Okay, and the second competition is the MIT AIQ challenge which I mentioned earlier, right? So this is not for image data. This is actually the graph data. So we represent, right? So each molecule is represented as a graph, right? The learn of graph neural network. And so we are able to achieve the first place at this MIT AIQ challenge. So this is collaborating with Dr. Srivan Jit's group at the Texas A&M University. So compared to the original solution without using this libAUC library, so we are able to improve the AUPRC by 5% and improve AURC score by 3%, which are dramatic. Okay, so So we also compared our libAUC library with other existing libraries. So as Harry mentioned earlier, so Google has developed this TensorFlow constraint optimization library, which can be used to optimize partial AUC, can be used to optimize average precision. So here we compare our libAUC library with the TensorFlow constraint optimization library for optimized AP. So the top two figures are for the CVPR 10 datasets. Left is for training data, and the right is for the testing data. And the bottom two figures is for the melanoma dataset for detecting skin cancer. Right. Again, the left is for the training data, and the right is for the testing data. And you can see that the blue curve is our libAUC library that implements the SOAP algorithm, and also with some set of other techniques from our recent SML paper. And the other two curves, the orange one and the green one, is the TensorFlow constraint optimization library. You can see that our algorithm on CVPR 10 dataset, we converge much faster and converge. Finally, we converge to the same solution, but we converge much faster both in terms of training and testing. On the melanoma dataset, somehow we cannot make the TensorFlow constraint optimization work. So on the training data, it does not work very well, right? So we converge to much better solution. And the testing data, we also can converge quickly to a good solution. But eventually you will see that because training performance is so good, we kind of overfeed the training data. So the testing performance eventually becomes worse, but we can actually select a good model by early stopping. And also we compare the libAUC library with TensorFlow ranking library. So TensorFlow also implements ranking library that includes set of algorithms for optimizing different objectives, losses for learning to rank problems, right? So that includes, NDCG, approximate NDCG, and the Gumbel approximate NDCG, and some list-wise losses such as the list net. So here in our libAUC library, we also support optimization for NDCG and top K NDCG, and which is definitely not focus of this tutorial, but we can see that our algorithm, the top three curves, right? So the red curve is our algorithm for optimizing the top K NDCG. The green curve is our algorithm for optimizing the standard NDCG, and the orange one is another variant. And you can see that our algorithm is converged to a better solution than these algorithms implemented in the TensorFlow ranking library. And also in terms of running time, we do not use more running time than their library. So finally, I just want to show you an example that running the libAUC library on the Shakespeare dataset. And you can see that it's very easy to set up your experiments by using the libAUC library. Right. So first thing, you just need to import some functions, or just import the libAUC library, right? And then the sixth thing, right? Second, the column here, just define your data sets, right? Define your data set, and also define your data loader. So this is also kind of standard. And this third column here is define your model. Right? Define your model, neural network model, and then we have implement functions for defining loss, right? For defining the optimizer, right? So for different losses, you can get the different loss, define different loss, and also for that loss, you get the define the corresponding optimizer. And then you do the standard training, right? So do the forward propagation, right? And then do backward propagation, call this loss to do the backward propagation, and then call the optimizer to do the update, right? So this is fairly standard. So you can also evaluate, right? So by using the corresponding performance measure. So it's very easy to set up your experiments on libAUC library. Okay, so finally, I want to mention some future directions, okay? But this is definitely not an exhaustive list. I just mentioned some interesting directions for you to consider. The first thing is to consider further improving the algorithms, right? I think that there's still much room to improve the algorithms. For example, accelerating the convergence, right? So the convergence may not be necessarily the optimal right now. How do we improve the convergence for different stochastic algorithms for optimizing those measures? right? And also we can consider new optimization paradigms, for example, bi-level optimization or federated learning for the bi-level optimization. So recently, we also considered using formulates partial AUC as a bi-level optimization. And actually in our recent SML paper, we formulate the NDC top K and DCG as a bi-level optimization. And you can do similarly for the top K mean average precision. Right? You can formulate as a bi-level optimization and then use our algorithm to solve that. But the question is, how do we solve this problem in the distributed fashion, in the federated learning setting, right? So this can be considered as in the future work. So another thing is, how do we make the algorithm more robust to the distributional shift, right? So you can see in one experiment, so this kind of algorithm, right? So optimizing AP, optimizing this AUC score is very good, right? In terms of training data, we can make the score very good, but if there is a distributional shift between the training data and testing data, if we optimize the AUC performance very well on the training data, it may not generalize well to the testing data, right? So one question is, how do we make this kind of algorithms more robust to the distributional shift? So another thing is, how do we make it more robust to the adversarial noise, right? So adversarial noise, adversarial learning has been studied a lot in the traditional empirical risk minimization setting, but not too much in this, AUC maximization framework. There emerged some recent work studying this problem, but there is still much work to be done in terms of adversarial learning for deep AUC maximization. So another thing is a feature learning. So me and we have talked about two kind of approaches for feature learning. One is end-to-end. It's a two-stage approach. So first, we learn the feature network by optimizing standard, cross entropy loss. And the second stage is to use the deep AUC to fine tune the network, right? So and also he talked about this end-to-end learning framework by the compositional training. But the question is whether there exists a better way to do end-to-end learning. So one question we need to consider here is that why deep AUC loss, optimizing the AUC loss from scratch does not necessarily give us better feature representations. So what is the reason behind that, right? And how do we address that issue in a more elegant way? So another direction is to incorporate the self-supervised learning. As I mentioned earlier, so this library, our libAUC library, also support the contrastive learning for self-supervised learning. And this library does not require you to use very large batch size, right? And recently, a group of researchers has employed self-supervised learning to learn feature representation first, and then use the libAUC library to fine-tune the network. And also they achieved great success. But I think there's still a lot of things we can explore using self-supervised learning to learn the feature, and then use deep AUC to fine-tune the network. Even though, and also we can consider using the AUC loss, using the NDCG loss to do the self-supervised learning is another interesting direction. So another thing is about the trustworthiness, right? So AI has been used in so many domains, and this trustworthiness becomes a very emergent issue, such as fairness, right? How do we make sure the model is fair to different, sensitive groups, right? So in terms of fairness, we have seen, some traditional fairness, but recently there are also some new fairness, such as AUC fairness, right? And such as NDCG fairness, right? All following in this kind of framework, right? So how do we optimize AUC subject to AUC fairness, right? So it's an interesting question. Another thing is, how do we make the model interpretable, right? So in the framework of AUC maximization, in the framework of X risk optimization. So the last thing is to consider more novel applications, right? So we have considered, medical image classification. We have considered molecular property prediction. What other interesting, what other important applications we can consider by using this libAUC library and for optimizing, different measures risks. Okay, so that's all we want to talk about for this library and future work. So turns out we ended this talk earlier, so we have a lot of time for questions. So if you have any questions, feel free to ask right now. We have other 3 speakers online, so please ask questions if you want. Thank you. Can you maybe go to that? Yes.
So for the real data sets, AUC the last trustworthiness, AUC fairness, right? Is there a notion of AUPR fairness?
Turns out, no, we haven't seen another notion of AUPRC fairness, but you can define similarly, similar to the AOC fairness, actually.
Okay. So when you speak of interpretability, what do you say with regard to trustworthiness?
So you can consider, similar problem that has been studied in the literature. So in terms of deep learning, people consider deep learning as a black box approach. And recently also, some studies trying to make deep learning more interpretable, right? So given this image, right, so you have a prediction. So why is that? Why do you predict this image as this class, right? So, and in this deep AUC maximization, as you can also consider when you make the decision, right? When you make this prediction, why do you make that prediction? Why do you, for example, for this example, the score is very large. For that example, score is very small. Why is that, right? So what kind of explanations we can get from this?
So are there any interpretability tools?
Huh?
Are there any interpretability?
No, there is no. I think so far there's no work on in interpretable deep AUC maximization. Yeah.
So typically in classification and all kind of visualization tools. What does it mean? The basis for decision.
Yeah. So that is one approach, right? So other approach people have considered, for example, prototyping type of scene, right? So use prototypes to explain the predictions of the network, right? So that is probably one thing we can also consider to incorporate into the deep AUC framework. Any other questions? We also will welcome questions from the online audience. So you can either type your questions in the chat box or you can also speak up.
Partial AUC and actually one way to discount. So is the partial AU bounds defined by the application or?
Yeah, that is defined. You're defined by the user, right? By the domain user. For example, in certain medical domain, so for diagnosing certain diseases, the doctor may require false positive rate to be less than some other bound. So that is defined by the user. Yeah. Yes.
What is the typical compare so you when you're comparing against the state-of-the-art methods, you use the same algorithm for different domains, or I don't get it. The same threshold doesn't hold for different domains in medical. For instance,
yeah, for experiments, we just experiment, different settings, different thresholds, right? And so if you use a set of thresholds, and you can also still tune that threshold in your algorithm to get the better performance. Right?
Yeah, what's the maximum imbalance level?
I'm sorry, what is the
What is
maximum?
the maximum imbalance level of data? Like you have a table where you show the
Maximum
imbalance factor.
Oh yeah. So I think depending on the setting, we could have very imbalanced data. You know, in the
1% in one of the papers, right?
what?
1%.
1%, yeah. So for example, for medical image, we have seen 1%, right? And for this molecular property prediction, we have seen even more imbalance, 0.2% of positive examples.
And were there any specific insights, specifically with respect to medical image? Observe. Yeah, I don't know. It's anything special when you take up medical images.
Any insights?
Yeah, any insights? Like usually the problem with medical data sets is like along with imbalance, there are often some sort of spurious correlation factors, right? Like your positive class, for example, will come from one hospital. So, like maybe this is on lines of what she was mentioning, that if you have some interpretability methods, then you are very sure that your performance is good as well as the metrics are looking better than the areas, so they should look at, right? So, what was anything along these lines part of your studies?
Yeah, so far no, we haven't done a lot of things. So yeah, I think that probably needs more people like you guys to study this type of approach for medical data, because we are not experts, you know, in that setting. We just consider this as a data set, employ these methods, right? So I believe there are a lot of things you can explore for medical data. So one thing I just want to mention here is that on the Shakespeare data set, so you know, the second place, which is the original or first place before our methods, they actually leverage domain knowledge in the medical data set. You know, there are you know, 14 diseases. There is a relationship between these 14 diseases. Maybe, you know, patient with one disease maybe should also have another disease, right? So they leverage domain knowledge. For our approach is simply data driven. We don't leverage any domain knowledge. So we still get better performance. So this means that if you leverage domain knowledge, then you probably can get even better performance. Yeah.
Thank you.
Thank you. Thank you. Thank you. So if there are no more questions, we can enter this tutorial right now. Thank you. Thank you for your attention. And thank you all for this online. Okay, you have a question? Yeah.
Yes. Okay. So you're interested in accelerating the convergence. Do you have any ideas on how to do that? And specifically, did you consider supporting for that? Maybe.
Yeah. Okay. Good question. So actually, yeah. So we do, you know, concern a lot on the convergence analysis, right? Because we want to make sure the algorithm converge. You know, so in terms of algorithm design, you know, our algorithm is, so we want to keep that in mind, that we want algorithm to be efficient, right? So to be as simple as traditional existing algorithm like SGD, like momentum, like an adder, and for other deep learning tasks, right? We want to be as simple as efficient as that. Right? So in our design, we try to keep that. We try to keep the algorithm as simple as possible, as efficient as possible. Right? So the Newton method you mentioned, yeah, it could be a method for optimizing these objectives, but
it seems too complex.
yeah, maybe, you know, it has more complexity, higher complexity, higher cost, so that we didn't consider. Yeah.
Okay. So, but parsing methods.
Yeah. Again, so I think this type of method, has been considered, right, for deep learning, but they're not as efficient, probably as popular as, you know, stochastic method like Adam.
In my assessment, the verdict is still open. I think still not in. So I mean, there are people working on more good methods for machine learning, for deep learning.
Yes.
Well, I mean, some of them are of the opinion that it can be very efficient to do it correctly.
Yeah, it's possible.
Yeah,
It's
but
possible.
that's why I was asking.
Yeah. I think one question is probably we need someone to make this happen, to make it available to the community, right?
Yeah.
Yeah. So that's also an important part. Yeah.
Okay. Okay, so but you're not actively.
We're not actually working in that direction.
Yeah.
Yeah.
Okay, I understand. Thank you.
Okay, thank you. Okay, I think we are at the end. All right, thank you, Yiming. Thank you, Harry and Mimi.
Yeah, good job, Iqbal. Thank you.
Yeah, I think a lot of people. Yes, great. Thank you. Bye.
Enjoy the trip. Yeah.
Yeah. Thank you.